So, good morning, everybody. Thank you very much for attending the talk. I'm also very grateful for the organization for inviting me. It's just a pleasure to deliver a talk in the topic. I have been asked to say that please write your questions in the chat so that we can ask them to ChatGPT. No, it's because the audio doesn't work. Okay. So if you speak on the mic, we are not going to hear you. Please just write the question in the chat. Thank you very much, everybody online, for attending, and also everybody who has come to the event. So in the last decades and a half, we have witnessed a revolution in information technology that has reshaped our world, right? The rapid spread of smartphones has connected the globe, and this was supported by the ubiquity of internet access and the power of cloud computing. This convergence has created a global platform that influences near every industry and touches every aspect of our life. Also, our understanding of data has evolved deeply as well, right? We now approach learning from data with a fresh perspective, uncovering insights that we could never think about in computer vision, natural language processing, clinical trials. And these advancements sign a clear shift, right? There's no way back. Even in theoretical machine learning, nowadays we choose the model after looking at the data, and this was completely forbidden by statistical theory decades ago. Right? So there's this idea of singularity that has been firmly buried in the minds of intellectuals and computer scientists of half last century, and they assert that a computing power available to humanity would be scaled by 1014 from 2005 to nowadays. So this forecast was delivered by stacking many fascinating speculations, right? So you have a look at the graph, it's in log scale, and you see that the distance between the apparition of art and agriculture is the same in log scale than the computer and PC. But the more philosophically accurate viewpoint is that what science has witnessed is a research community that creates and exchanges digital artifacts following new models of knowledge. And this is a superpower that we are living as researchers. So one case is ChatGPT, right? So if you look at the numbers, what took Spotify 4 years to achieve, which is to reach the barrier of 100 million users active by month, ChatGPT did it in 2 months, right? And as we see here, nowadays, so this report is taken from April this year, so this month, and it has already 180 million users. So in just 5 days, 1 million, the threshold of 1 million users was surpassed. So let's have a look at the historical context a bit of what's going on right now. So we could trace back the origins of the trend we are living to the times of Turing, and we have to also acknowledge all the sort of important algorithms that rise in the 20th century that make AI work. But we could trace back 2003 when Joshua Bengio and company had the idea to use the same neural net to accomplish a variety of tasks, right? So this was the first time that this idea of using the same architecture for different actions has been tried. If we move on to 2013, so in 2008, two milestones happened, but the most important was the use of pre-trained word embeddings. Until 2013, where words have started to be seen as vectors in an Euclidean space. Right? So what happened here with Word2Vec? So if we imagine that this is Rn, and we call phi Word2Vec, the map that Word2Vec codifies. If we look here at phi of swimming, and imagine that it's this point, right? So we embed a word in Rn, and we look here at phi of port. Then, if phi of bachata is here, what's surprising about Word2Vec is that by guessing, is that the geometry of the space tells us meaningful semantic relationships. So phi of dense will show up here. So that we can arrive here, but by going here and here. Okay. This has been a true revolution because it was the first time that we could geometrically interpret words. Yeah.
This should be the other way around, right?
Maybe, yeah. Just it's just to say that the inner product that phi encodes respects the geometry of the pre-embedding, right? And something that I like a lot to speak about is about a paradox that shows up here. So if you look at where can I get an eraser? Maybe I can do the other one. I can do this. If you look at so imagine that d is the distance that is inherited from this embedding, right? From the inner product of this embedding. So if you look at the distance between sheep and white, you expect this number to be bigger than the distance between sheep and black, right? Why? Because if you look at the geometry of words, white is closer to sheep, right, than black. But if you think it empirically, this is completely the opposite, right? Why? Because language models and embeddings see way more black sheep than white sheep. We never write white sheep. Right? This is like a paradox that rises when changing from the population level to the empirical level. Anyway, then in 2014, David already spoke about RNN. So it represented the use of end-to-end architectures to learn both input and output representations. And in 2014, seq-to-seq was the first time that neural nets were able to manage variable length inputs and outputs. In 2017, as Roy spoke about it in the last session, the transformer architecture marked a huge breakthrough in terms of being foundational for all the models that would show up later on, like GPT, BERT, T5, right? And what we are going to speak today about are these two milestones, right? So the operation of generative pre-training, and 2020, the operation of few-shot learning. And we are gonna see what's the meaning of both articles. Okay, so just to mention that the story does not end in the border of the chronological axis here, because just from Thursday, Meta has launched Llama 3, which is apparently pretty similar in architecture to Llama 2. But the difference is that it's trained on a way bigger text corpora. Okay. So let's start with with the paper that opens the era of GPT, right? And if you look at the initials, GPT comes from generative pre-training. So the narrative of the paper is about justifying that natural language processing, contrary to what we believe nowadays, which is that it's only useful to answer to the questions you prompt the chat. So this is a lie. At the end, it was born to make textual entailment, which means establishing logical relationships between sentences. It also involves document classification. So if I give you this fragment of the speech of a senator in the United States, does this speech come from a Republican or a Democrat senator? And of course, the question answering, which is like the king of the tasks nowadays, right? And they say that, okay, there's a lack of data which is that, right? So we have lots and lots and lots of texts, but we don't really have labels to put on these texts so that we can learn how to perform these tasks specifically, right? And they argue that the solution to this is to carry on with a first step that has to do with giving the model a general understanding of knowledge, and a second step that has to do with fine tuning, where we can take a small supervised, we can take a small labels data sets where we have the questions and answers, and we can do a second round of training. So this is the main idea. So how does GPT work? So at the end, what we have is the task of language modeling, right? So we model, so if we have words U1, U2, UN, we train a language model which is indexed by a composition of transformers who live here in theta, big theta, times an Euclidean space where this matrix W lives. And this matrix W, what represents is what Roy spoke about last day, which is the embedding matrix, right? So it looks like the model has two components. So the conditional distribution of the next token is given by some sort of composition of a first layer that is something similar to what we spoke about word Schubeck, right? We put the words in a high dimensional space. And then we start to do compositions of transformer layers, right? Until theta n. But we have to finish with another one, which has to do with projecting back on the space of tokens, right? And this W is orthogonal, so we can just do the transpose. I want to make emphasis on this because understanding that going first to R in GPT-3 are 12,888 here, and then going back towards plays a fundamental role in how ChatGPT is hard-coded nowadays. Why? Because in the first stage, we train all these parameters, the transformer layers and the embedding. But in the second stage, when we do fine-tuning, what we are doing is giving the model a sequence of pairs. So a question and an answer, a question and an answer, a question and an answer, or a text from a senator, and if it's Republican or Democrats, and another one, right? And in the second stage, what we do is to plug in the estimators in the first phase and leave this open to training. So gradient descent only acts in the last one. That's why fine-tuning is affordable. because we are only attacking this matrix. Okay. So yeah, this is the main idea that we are kind of obtaining the minimizers from a general first stage, and then we plug them back, except from the last layer, which is going to be the responsible of the task of the particular task. And I put a photo up there of Andrei Markov because as you see here, you think, okay, the probability of the next words given the previous one only depends on the k before, right? So this reflects very well how Markov chains were born, because they were born when Markov was studying Russian language, and he studied the probability of a letter showing up even the previous.
My apologies.
Yeah.
If you can allow me, I just would like to, of course, we have to take into consideration that this is, so to say, the initial model. And of course, things have much evolved, since then. But many experts, for example, arguably Jan LeCun, they clearly stated, that the future, of deep learning, is unsupervised. So what I find a little bit, what I find a little bit perplexing and surprising, because fine tuning, is a much more complex process, and as we all know, unsupervised techniques, they involve a larger degree of subjective criterion. So then, why make the choice, to opt instead for supervised fine tuning, when with semi-supervised or unsupervised techniques, we could have potentially reached, a larger degree of subjective criterion, which could have given us, a wider perspective.
That's true. I mean, I have to say that this comes exactly from the foundational article of GPT-1, right?
Yeah, of course.
So, of course, nowadays the fine-tuning strategies have evolved a lot, because how BERT is fine-tuning is completely different story as how it is, right? So thanks for the comment.
Yeah, and my apologies. Yes, this is indeed, what I said before. I understand completely that this is indeed the foundational model, and of course, since then they have evolved.
Yeah, of course.
Yeah.
So with this slide, I just wanted to make clear that the milestone of GPT is this two-phased philosophy, where first the model has a general understanding of the structure of language, and then we specialize it. So this is the.
And next day, Victor will specify a little bit more on what.
Exactly. Okay, so this is just an illustration of what I showed. We have the words. We embed them in a high-dimensional space, thinking in word back, the fight, right? And we apply a composition of blocks, and we go back to the word space with the transpose of. Okay, so now let me try if I can just yeah. So let's go now to the second article, which I guess was the introduction of GPT-3. So for the first time, so as you see, it's authored everything by OpenAI, and they speak about phenomenology related to the fact that going on. Yeah. So yeah. Large language models, and especially the larger they are, the better this works. If I give them some examples of a task, so for example, to go from English to French, right? I give it in the prompt, so I don't touch the weights. I do it in the prompt already. In the message I give to ChatGPT. If I provide some examples of the task already in the message, the model is able to guess the task. So this is called a few-shot learning. One-shot learning is when we only provided an example in the prompt, and zero shots happens when we don't really need to give any example. We just ask for a question like correct the essay I attached in PDF. And this is opposed to fine-tuning in the sense that in fine-tuning, so when we touch the last matrix, what we are doing is to provide a labeled corpus of text where we give clues to gradient descent on how to update the weights to specialize the model in a task. Right. So let's have a look at an example of few-shot learning. Well, first I just wanted to show you a skeleton of what's GPT-2. Maybe we can do this. Yeah. So desktop. Yes. So do people online see Spider?
Yes.
Okay. So this is being serious.
But not the people.
Oh, really?
Okay.
Okay. So what's going on?
No, it's okay, it's okay. Maybe you have to stop sharing from that one.
This might be a bit dangerous.
No. No, the problem is, don't worry.
Okay, I just wanted to comment that. I mean, we don't have to look at it. That this is like 60 years of code, right? And what we see here is the function MHA, which is here, which is the mathematical attention. We see here the transformer block, and we see here GPT-2, right? Which is the function that builds the final model based on the other definitions, right? And we just have the function generate, which is like the reply.
The what the?
The reply of the prompt, right? So we now call GPT-2 from the terminal. And please have in mind that this is 2000 and oops. Yeah, I mean, we are using the terminal to call GPT-2, and it seems like we are in the Middle Ages, but this was a few years ago. So we can ask him or her or whatever the following question. So I asked for the people in the room, what genre do these artists play? And I gave him some examples. So I said, Ice Cube plays rock. Ben Clock plays techno, and Bad Bunny plays reggaeton. So these are the few short examples. And then I asked, what genre does Tupac play? And we ask. Rating. And it says Tupac Shakur, it plays rap. Okay. So what we do here is to not touch the weights of the last layer in a trial to specialize it in a task of guessing what's musical genre that an artist play. We just did it in the prompt, and this is a three-shot learning because we gave 3 examples. Okay. So now I would like to speak about the mathematics of what's behind. I can stop sharing screen probably. Yeah. And I hope, yes. Do people online see slides? No.
I think. Is it sharing from there?
What?
Is it sharing the screen?
Let me see. So
Maybe stop sharing in the green button.
okay. Yeah.
I can find it. Oh, yeah.
Yeah. No?
Yes.
That's right. Perfect. So now it's control was okay. So we have first we have to define first what is pre-training, right? So, as always, in machine learning, theoretical stats, what we see is that we are in an empirical risk minimization problem with a constraint, right? So we look in a model class, which is this big theta, and it's a space of transformers, right? Because we have the attention layers and the multi-layer perceptrons that come after the attention, as Roy mentioned. And we have to bound the number of heads. We have to bound the number of layers that the multi-layer perceptron have. And we have to restrict ourselves to a ball in this space. And I don't write the definition of this norm because it's not very friendly. So what's going on here? We have a space of transformers, lots of them, which are indexed by the configuration of the weights. Right? And we restricted ourselves to a particular ball here. That we call, and this is encoded by these restrictions, right? So yeah, sorry. So yeah. Sometimes in math, it happens that there are like super beautiful concepts that don't make a lot of sense, but they are super useful and theoretically deep. Like how can we count an infinite number of objects? But thank God there are lots of brilliant minds in our work, like Kolmogorov, who came up with the idea of the covering number, right? So the idea is about I can measure how big is a space by placing a lot of by counting how many balls of a given radius do I need to cover the space where my transformers live. Okay, and the logarithm of this number turns out to have a lot of relation with the theory of thermodynamics because it's called entropy, right? So what we see here is a first inequality that we can check in the book by Wainwright, which is a great book, by the way. And we see that we can bound the logarithm of the number of balls we need to cover the transformer space by the dimension of the space times the logarithm of 1 plus 2 over the radius of the balls. Okay. So let's have a look at this and let's see if we can reach a conclusion using the formula. So what's beautiful about the theory is that we can reach really deep conclusions just by combinatoric, arguments that come from combinatorics. We just have to count. So let's count. Let's see. So this is the multi-head self-attention mechanism that Roy introduced the previous day. And we have to remember that we had three matrices, right? The values matrix, the Curie matrix, and the key matrix. So we have three matrices. And each of them have as many elements as the dimension of the embedding. So it's a matrix, it's D squared, right? Because D is the hidden dimension. And we also have to multiply this number by the number of heads, right? Which we call n. And we cannot forget about the number of layers the transformer has, which we call n. Okay. We had something left in the formula in the previous slide, right? The logarithm of 1 plus 2 over delta here, right? So we already have the dimension, and we still have this. Okay, so now you have to believe me that there's a mathematical notion called the Lipschitz constant, which whose magnitude tells us information about the roughness of the space, right? So the bigger the Lipschitz constant is, the more bad behaved the functions inside of the space are, right? So intuitively, you can think that the radius of the balls goes with 1 over the Lipschitz constant, right? Because the worse, the less smooth my functions are, the bigger the Lipschitz constant is, so the smaller balls I have to use to cover all the space nicely, right? And now you will trust me in that the Lipschitz constant for the space of transformers goes with L. Okay, so here we miss. So now we can use this inequality that log 1 plus x is less or equal than than x, and this holds for x x greater than -1, and we can just plug it in the inequality here, right? And what we have to do is to place here a square. All right. So now, by a very famous theorem that is inherent to a lot of proofs in empirical process theory, we arrive to a bound for the excess risk of in-context learning, right? Here we have what we see there. And here, by the chaining lemma, I don't know if anybody here is familiar with chaining. A new number shows up here, which is chi, which encodes that the inequality here holds with probability 1 minus chi. So the smaller chi is, the worse our bound is, right? And here, does anybody have an idea of what does this resemble, this term? So this is the fast rate of linear models, right? If you take here, if you take the typical estimator of the slope, which is x transpose times x minus 1 times x transpose times I, and you have a look at the excess risk in expectation, it's straight forward to see that the vector inside of this norm are d independent random variables with variance sigma squared and zero mean. So you're right, because we are assuming that the grounded truth is linear there. So suppose that P is almost surely well posed. So this means that the prompts are linear. We are giving ChatGPT a cloud of points which behave linearly, right? So this poses a sensitive question about what's gonna be the future of many data science departments in industry, right? Because until now, okay, we thought that only very mechanistic jobs were going to be replaced by AI, but suddenly we see that also a statistician that runs a clinical trial is threatened by a transformer, right? Because as we see, they are able to perform linear regression. Okay. So we can discuss about this later. Yeah, so this was meant just to give you an idea of the escalation in magnitude what happened since the first version of GPT until 3. Also, the technical specializations. So you see that what's the evolution from 1 to 2? We passed from million to billion, and GPT-3 is already 100 times. So yeah.
The first line of each of the versions, like for example, 768 dimensional word embeddings means that
the
one word, each word goes to 768 dimensions.
One word is encoded in a vector of size 768. Yeah. So it's where the phi of the word Subek ends up. Right? Yeah, exactly.
So is it known how these dimensions influence the geometry that you were mentioning before?
There's a lot of research going on, but of course there are a lot of open questions on how do they interact with the rest of the model. What's going on with sparsity? I mean, is R to the 768 too cold to host my words? So yeah, but of course there's a lot of research going on.
And the third line of each of these, like 512 token context window, means that the
Markov chain.
For each window, for each word, the 511 before are relevant.
Exactly. So if you go back to the model, where is it? Yeah, so it's this K here. It's the window. So it's this K here. It's the magnitude of so it's the order of the Markov chain. So how many words do I look back to create a context?
My apologies.
Yeah.
I just had a question. When you mentioned, my apologies. If you can go back, to the formula when we had T multiplied by sigma square. This actually, caught my attention a little bit. When you, and I'm sorry, because I needed to reflect a little bit, before formulating the question. So when you mentioned the word linear, linear often, of course, not always, but is associated with Gaussian processes. And I see this a little bit contradictory. Coming from an empirical evidence point. Because basically, ChatGPT, it has information, on nearly everything. So this is not strictly, a Gaussian distribution. So then, I do not understand very well how this linearity, and possible association with Gaussian distribution is here.
I tell you. Thanks. So the main point is that is to remember always the two-step mechanism, right? So this works under the assumption that in the few shot phase, when we prompt stuff like x equals 1, 33, 22, 5, y equals 1 again, 11, 17, and 8, and then we put here a /n thing, and then we ask about so if xm plus 1 is 80, what about yn plus 1? So this is assuming that we are giving ChatGPT this prompt, that we prompt a database that behaves linearly. And this is the part of the convergence rate that corresponds to here. So this part, of course, does not have anything to do with linearity. What matters is the second part of the rate that assumes that you are prompting numbers that follow a linear model. But in the same paper, you also see rates for when you input high dimensional vectors, and they give a fast rate for the lasso. They also give a rate for the generalized linear model, for reach, for a lot of algorithms, for a lot of base truths that are encoded with pi there, right? Which is the distribution of the prompt, not of the words in the pre-training phase. Did I answer your question?
Yeah, absolutely.
Thanks. Okay.
Thank you.
How many time do we have left? Okay. So yeah, GPT-4. Okay, we see that the technology is confidential. We have no idea about what's going on there, about the architecture. There are some speculations in blogs on the internet that we can find out. But we do know about the context window in the turbo version, which is the latest. And we also know that it involves order of trillion parameters. So, yeah. Okay, and I would like to book the last minutes to speak about delicate topic, which is to perform causal inference with text. So what's going on here? Imagine that you want to run a study where you want to guess what's the impact of the writing style of a lawsuit, una demanda, in the probability that a judge decides to put a person outside of their home, right? And I took the name of this word in English, which in Spanish we know is desahucio. I don't know if anybody in the audience knows how desahucio is said in English. Eviction. Okay. So, of course, judges have their stereotypes about people, right? And they encode them in style, but also how the language of law is encoded affects both the sentence and the decision of the judge. And the sentence. The legal text itself. And we find ourselves in a map that resembles us a lot to the black sheep issue at the beginning, right? Because there are a lot of background mechanisms going on that for sure distort the relation that we see between the writing style of a text and the decision of a text, right? So I'm going to speak about two strategies that have been carried out until now. So the first one, the first one is a work from 2019 where they basically fine-tune BERT. So BERT is a language model that works in a similar way as ChatGPT in the sense that it also involves transformers, but the self-attention heads are also allowed to see the future. So it's not masked, right? It can also see what's going on after the word I want to predict. Whereas ChatGPT doesn't. Yes.
ChatGPT doesn't?
Doesn't.
I mean,
if you remember the model, we spoke about a Markov chain, right? So we speak about the probability of the next token given the passwords. Yeah. Doesn't see UI plus 1. It sees UI minus 1, UI minus 2.
but you can make forecasts about you.
Of course. But in the training phase, the self attentions are masked. They only allow you to see the previous token. So the likelihood, let's say, is encoded in this way. While in BERT, it's allowed to see bidirectional representation. So what they do is essentially to make use of a super classical theorem of causal inference, which essentially says that if I know so this is a drug I give to people in a trial, and this is the counterfactual time of people who don't take the drug, and this is the counterfactual time of people who take the drug. Then, once I know the treatment, the covariates do not have anything to say about what's gonna be this time or this survival time, right? And the theorem here says that any propensity score can replace X. So suddenly it's the first time that a highly dimensional issue was shrunk into a one dimensional one, and it simplified a lot observational studies. So what they do here is to change B by BERT. They fine-tune BERT with an objective that aims to predict the propensity score and also the survival times. And with this, they just create embeddings which we can use to account for confounders. And it's a clever strategy. They even provide some asymptotic theory. And to finish, I'm just going to comment on this. So here what we see is the classical semi-parametric partially linear model where the confounders both affect the response and the treatment, right? So I start giving a drug and not giving it to people in order to have a look at if the survival time improves. And I see that it does, but maybe it's because I gave the drug to younger people. And that's what's encoded here, right? That age affects both the survival time and the treatment. So what we see here is that maybe I have magnetic resonance images that compel me to give a person a drug or not. And the magnetic resonance images are also influenced by the true state of the person, so that the relationship between the treatment and the outcome is confounded by images and text. And they basically introduce also BERT to adjust for. So X here is text in the paper. So for them, text is a confounder they can adjust for in a semi-parametric way. And this is February this year.
This is what?
February this year.
Oh.
Yeah, just one very small question.
Yeah.
Because you are speaking about causal inference, and of course, what you mentioned has to do with average treatment effect. So of course, as you know already, we have the local treatment, local average.
The conditional one, right?
The local one, which is kind of like basically, I mean, it's essentially a decomposition of the average. So I was just wondering, if this kind of strategy, I mean, in this scenario, it would be a kind of equivalent, for the latter, for what we call local average treatment effect. So if there is, some mathematical similarity,
So this resembles to CATE, to the conditional.
Okay.
Because if you look at the orthogonalized score, then it resembles a mean function of the y and the d, right? But I would have to look deeper in the latter idea. Thanks, that's a good point.
Yeah.
I would have to. That's the way. Yeah.
For this to work, you have to assume that there is no other causal path that goes from X to D without going through images or texts.
Exactly. So there's not backdoor.
Yeah. So you're conditioning
on
all
the confounders are encoded in text. That's
in the test that you measure.
In your text of your hospital. Yeah. So thank you very much, and I hope that this ignites a nice discussion, no? Any questions?
Could you go back to the in context regression?
Yeah.
And could you rephrase it for human beings?
So,
Could you give the Ubuntu version of?
yeah, the pseudo free. Okay, so, okay, what's going on here?
I mean, human beings like me. I mean,
Okay, so,
all professors.
let's go back again once. So, yes. So the theorem is about in the excess risk. So excess risk is how well does empirical risk minimizer, which is the minimizer of an objective, how well does it do in comparison with an oracle? Right? So the oracle is the best approximation of the truth, and we write it like this. So the best transformer in the space of the same laws. Okay. So the theorem is about giving a bound on the excess risk, is the name of this. Okay. When instead of giving the transformer words in English and in Galician, so instead of saying Sechoiva is rain, Rua is street, and Bico is a kiss, then what's Fuchica? You write it here. So instead of words, you write numbers that follow a linear model. So you put 1 goes to 2, 2 goes to 4, 3 goes to 6. Where does 7 go? So the theorem says that if the numbers you set up in the prompt are well behaved in terms of linearity, the first line of the assumption, then you get the fast rate of the linear model and the rate of pre-training. So this is very beautiful because it splits the two-stage philosophy of GPT, right? The pre-training, which is like the general understanding of the structure of knowledge, and define the few shots.
What is a small n? Is the number of
So small n is the number of tokens in the pre-training, so in all internet. And n is the number of examples you need. Now that we have time, we can see where does this come from. So if you assume that the numbers you put in the prompt follow a linear model, then you can say that the predictions minus the truth, it's one step thing, they are equal to this. Times the residuals. But you know that in linear model, what you're doing is to project the response onto the span of the columns. So this is a projection that I can write like this, and P is orthogonal. We can do this. And P is orthogonal, such that, so we can. Okay, but if you take the norm, then because the two norm preserve orthogonality, you can take one P out and you write this. And it can be shown that the components of this vector have this covariance and they are also zero mean. So at the end, what I have is the elements. So if I take the expectation here, this is the second order moment, right? I can put a square here. and this is d times the variance. And if I look at the risk, I divide over n, over n, over n. Oops, what did I do? My God, yeah. D sigma squared over n, which is the rate here. What happens is that when you have the fast rate of the lasso, so you can bound the eigenvalues of the covariance and all the story, you have the fast rate of the lasso. So you are able to split the pre-training from the fusion. So, issue here, I mean, all pharmaceutical research is carried out by regulation with linear models. So, what's going to be the future of a person that spends a lot of time in front of data that has been gathered in a trial, looking at a model, if a transformer can do it for you? And suddenly, I mean, we knew that professions that have to do with software were threatened by AI, and mathematicians were super pride about it, but now things change. So now there's bread for everybody. And yeah, I mean, I think that this opens the debate of what's going to be the future of data science departments in the companies, because it's clear that, I mean, this theorem is from 2023, it's last year. But for sure, there's going to be more research on how to automate model selection, post-selection inference. So how much did my transformer look at my data before picking a model and putting it there? I mean, this has just opened a waterfall.
And what about nonlinear?
Non-linearities. Being honest, I'm not sure about if they would interact with the pre-training phase, because it's also non-linear. So I don't know if there would be even an identification issue, but what's the definition of identifying a prompt? The model behind the prompt, right? There's an article that speaks about the fact that prompting is equivalent to do a tiny gradient descent step in the pre-training phase. Probably there's people doing some research there, almost surely.
And what are the assumptions here with respect to the pre-trained model? It says 3 heads, just attention only. But any assumption on the training, like there's like, because training will converge to a local optima of whatever loss function you have there. I mean, it seems very hard to prove this.
Yeah, but I think that the key is that they assume there's no multi-layer perceptron.
Yeah. So there is just attention.
Yes,
And
exactly.
there is, but there can be more than one layer.
Yeah, of course, but it goes logarithmically with the number of the length of the prompt of the message you give to ChatGPT. So n is inside of the logarithm. K is the conditioning matrix. Sorry, the conditioning number of the covariance. So K is alpha plus lambda over beta plus lambda, because they show this also for the ridge. And lambda is the regularization of the ridge, and alpha is the minimum eigenvalue, and beta is the maximum eigenvalue. But in low dimensional scenarios, you just forget about this. And what plays a role is the number, so the length of the prompt that shows logarithmically in the number of layers you need in the pre-train. So yeah, of course, what's the point of having to choose layers according to the length of the prompt? But this is an asymptotic result, right?
Yeah.
I
Yeah.
was wondering, if you could elaborate a little bit more, on the previous question, that I made, between the relationship, between linearity and distributions, and what I mean by this is that, clearly, our natural language, is of course, non-linear, and of course, this is a complication, because, for example, we tend to use some words much more
Sorry, yeah.
yeah. So,
Sorry about that.
yeah, that's fine. It's fine because, of course, we tend to use some words much more prominently, and of course, as in text mining, in natural language processing, there exist techniques, to overcome this a little bit. For example, with lemmatization, with tokenization, so we can more or less, linearize this. If, for example, if we remove, for example, if we use a lot of in, of, all of these.
Yeah, inverse weighting,
factors.
right?
Sorry?
Inverse weighting.
Oh,
So
no,
you-
no. I'm speaking more, from a linguistic perspective.
Yeah.
So what I mean is that by means of, for example, lemmatization or tokenization, we can more or less, linearize this, by removing, the less relevant, for the context words, and for example, if I say, okay, can someone come up with a simple phrase? I don't know. For example, I don't know. Let me think just a second.
Yeah, of course.
Uh, for example, cars are often gray. For example, so maybe if often, is a word that is prominently used, so maybe, we can remove these words, and if we just focus, the fact, on the linguistic facts, that cars, let us suppose, the cars are gray, so by this means, what I mean is that we can linearize this. But nevertheless, I'm very interested, in how this impacts, the whole distribution, the whole point of the distribution, because in some way, mathematically speaking, we are, when processing, all these linguistic input, we are going we are going to have spikes continuously, for words that are used more prominently, and of course, this affects, the form that a distribution takes. Do you understand more or less my point?
Yeah, but yeah. So that's the main point of an embedding, right? So okay, one-coded coding is something very sparse, right? Because you got ones every 1,000 zeros, and you have a very sparse object that encodes a reality which is not so complex, right? What do you achieve with an embedding? To transition from an object which has a lot of trash info to an Euclidean space where the notion of proximity, which is given by the embedding and the product, tells you about the semantic and grammatical relationships of the words. Right? So the point you make of spikeness, yeah, I'm sure that modern models work on the embedding phase with the techniques you mentioned. But in terms of probabilistic behavior, I would say that what's going on is that all the tokens concentrate around a subspace in a smooth way, and then as the transformers are applied forward on, these lower dimensional manifold, if you want to call it like that, is conserved. So even though you apply several layers of the transformer, you are still in a low dimensional place where when you go back to the tokens with the W, the W transpose, nothing happens. So I think there's some sort of high dimensional phenomenon going on here, but
yeah, basically, there is still a lot of space for research. Yeah,
exactly, of course there is.
Yeah.
a lot.
And one final remark, actually, your presentation was fantastic, also.
Glad to hear that.
Yeah, absolutely. Yeah. Also, regarding the part of causal inference, but immediately, when I saw, causal inference, I mean, I was like, oh my God, I mean, what is going to happen? Because what I noticed, recently, I had to give a course, on machine learning, both on basics and on advanced, machine learning, and what I noticed, is that even, by many renowned scholars, particularly, in causal inference, for example, by Imbens, among others, so what seems a little bit problematic to me is that nowadays, I mean, this is of course not a problem that we are having here. I'm speaking, more in general, what is happening, in the academic world. What I find a little bit worrying is that, there is a lot of conflation, when causal inference, is applied, with deep knowledge, of statistical learning or machine learning. Especially, I see a very strong conflation, between statistical learning and machine learning, because as we know, statistical learning, it relies mainly, I mean, it should be applied ideally, when we have some intuition, about a concrete distribution that we are going to make use of. Whereas, in machine learning, we have much more flexibility, with the whole theme of distributions, so again, this is of course, not anything, that is happening here. I mean, we are having a great session. I think, but what is happening, a little bit outside, in the academic world, when I hear, some renowned researchers, who are recently, starting, to explore, statistical learning or machine learning, and when these kind of conflations, they happen, and they get, of course, a lot of attention, for saying a lot of these things, so I find this a little bit problematic indeed.
Yeah. So, I mean, as you mentioned, there's a false belief that causal inference started yesterday, and that's not true.
Yeah,
As you mentioned,
absolutely, yeah.
economists have been thinking and designing their estimators, which are really complex, by the way, since around time ago. What are we starting to see nowadays? Quite weird theoretical results in terms of how the complexity of the model interacts with compounding. So, for example, what you mentioned about this trade-off you have between classical statistics and machine learning about the distribution, the flexibility of the model. I mean, I don't know if anybody here in the room has heard about the lava estimator. So lava basically has a theoretical result that says that the dimensionality turns out to be a blessing, in the sense that instead of spoiling the rest of your estimator, it helps. So the more densely the confounders act on the covariates, the better you will do. But they have to act a very little, but on a lot of them. So the dimensionality here shows up to be something that runs in your direction. Very weird.
Yeah, just to finish, last 30 seconds, so now that you mentioned economics, of course, as you also know, this, the whole thing of causal inference, it did not actually, even start in economics, it started, with a study, of the, I can't remember the disease exactly. I think it was malaria, which was, no, not malaria, but some other disease, that it was propagated, by water, in London, so it actually, then of course, it transcended, into economics, especially into evidence-based economics, but it has, it actually, started in what we would call now, health economics, of course, there was no such definition, back then. And finally, just to finish, I will definitely thank you very, very much, for this suggestion, I will definitely look into lava, this is a term I heard, but I haven't looked into it, and regarding economics, now that you mention it, a very promising direction, that I see, is especially, the possible applications of Q learning, for economics. Sorry?
Yeah, so it's a branch of reinforcement learning. right?
Yeah, exactly. Yeah,
Learning
exactly.
for what?
Yeah, I'm going to explain. Yeah, just 20 seconds. Yeah, so basically, Q learning, I mean, it's a very interesting concept, in advanced reinforcement learning. And basically, the whole idea is that for Q learning, unlike for other types of machine reinforcement deep learning, we do not need a model. So basically, in Q learning, we only have a state space. Okay, so we are only working with a state space, which is defined only by states and actions.
But you need to parameterize the key function, right? And that's one of the
Yeah,
issues of learning.
yeah, absolutely, yeah.
So you need a model, right?
Sorry?
So you need a model, indeed.
I mean, it's not, but I mean, it's not.
It's often the obstacle.
Yeah, okay, yeah, but it's not a model in the sense of being a complete traditional model. Okay, of course, I mean, you have to specify the parameters.
A model of the real world. You need, I mean, you have a model of the value function. It's not a model of the real.
Okay, so not about the
Model
Markov process, right? Okay,
Yeah,
of the MDP. Okay,
yeah,
yeah.
exactly. Yeah, basically.
Sorry about the
No,
misunderstanding.
no, it's fine. No, basically, as David very correctly, as he points out, so what we seek, is not to sort of impose a model, in order to try to understand, some kind of reality. So of course, what you mentioned is very important because, there are some parameters that we have to calibrate. Of course, so there are some elements of the model, but it is not strictly a model, insofar that, we only have, I actually have some slides on this, if you're interested, I can show you later. So basically we have this, I can't remember the name, how was it, transition difference, I think, could it be?
Temporally.
Temporal difference. Yeah, exactly. Yeah. So basically, it's about, starting at one given point, then we apply, temporal difference, and then, it basically, it proceeds, in a sequential way. Yeah. So basically, we have one state and one action, and then, we have a posterior state and the posterior action. So of course, as you mentioned, there are some parameters. Of course, we need to make some adjustments, for some parameters. But as David said before, this is not about, trying to explain, some kind of reality, by means of a full model.
To me, this resembles a lot to the same story that happened in causal inference in 2016, where so I mean, up to then, identifiability of the model was like the mantra, right? So you have to perfectly know what does it mean each a parameter, and you have to make sure that asymptotically, even in the presence of confounding, your estimator converges to the true value that. So there's a one-to-one correspondence between model and reality. But since then, research started to transition through causal regularization, right? So they started to think it as a problem where you pay the price of bias in terms of identifiability. So I will be honest about the amount of information coming from different environments, which is the typical instrumental variable assumption in econometrics. I'm going to be a bit chill about what do I know, and then I do it through regularizing, right? And this has been a huge conceptual shift that is leading now to a line of research called approximate identifiability. In fact, David and I had a research on that last 2 weeks ago on econometrics, right?
Yeah.
But of course, there's a fascinating waterfall of theoretical and practical notions that will interact for sure in the next decades. It's really exciting.
Yeah, by the way, I'm
We
not.
have a question of another.
Sure.
Maybe we can go on later in the talk. Yeah, please.
But where this is published,
Sorry?
where this theorem is published.
I can show you the paper, yeah, sure. So it's called Transformers as Statisticians. Actually, it's super late. Okay, wait. Transformers as statisticians. statisticians. Yeah. It's an archive.
Okay.
So they basically,
Can you state to write the number?
sorry?
State at the first page to
Yeah.
write the number.
Yeah, of course. So it's, yeah. 2,
The
3.
conference paper,
Sorry?
it's a conference paper.
No, it's long. It's long.
Super.
4, 6, 3, 7. Yeah. And as I told you, they basically come up with an embedding, with a way of embedding the prompts, and they derive rates for the
Hugh
read.
by.
Yeah.
The author is Hugh by.
Yeah. Exactly. Yeah. By. Let me see if I misspell it. Yeah. By.
Hugh by.
So as you see here, they derive the rate for the reach, and then they have this rate for when you didn't pre-train the transformer. Then they also frame it well the classical minimax based theory with GLMs. What else? With the lasso, as I told you.
Oh, yeah.
Question.
No. Thank you.
Thank you for inviting me. All right.
Pidiendo por